Hello dear friends, I am going to take your 10th lecture of CMOS logic family. This is regarding the paper PPH 1802 Digital Electronics Logic Family. We have already studied about the TTL logic family and now we are studying a CMOS logic family. We are comparing two simultaneously. So in a CMOS logic family, first lecture you have studied about how to construct a NOR gate and NAND gate using a CMOS inverters. And then we have studied the two important characteristics of the CMOS logic family, and that is a propagation delay time and power dissipation. And in power dissipation also we have studied about the static power dissipation as well as the active power dissipation of CMOS devices and its limitation that CMOS devices cannot operate at higher frequency, otherwise the power dissipation increases, active power dissipation increases, and it will be comparable to the TTL. So these are the things we have studied about the CMOS devices. Now we are going to study the detail of CMOS characteristics. CMOS devices, that is 74C00 series, are guaranteed to work reliably over a temperature range of -40 degrees Celsius to +85 degrees Celsius and over a supply range of +3 volt to +15 volt. That means compared to the TTL, TTL can work from 0 to 70 degrees Celsius and exactly 5 volt plus or minus 0.25 volt. That means plus 5 volt regulated power supply is required for the TTL. In case of the CMOS, the VCC range is very large. That is from 3 volt to 15 volt. So even if it is slightly unregulated voltage is there or somewhere you are in a circumstances where voltage fluctuation is going to be more, then also there is no harm to the CMOS IC. Second things, its temperature range is wider than the TTL range. This temperature range is -40 degrees Celsius to +85 degrees Celsius in case of the CMOS. That means -40 degrees Celsius is very low, extremely low. You can say that in the circumstances where Canada or Antarctica or somewhere, and +85 degree near the equator, etc. also this IC can work reliably, so no problem. You can mostly utilize this commercial applications IC only. That is more than enough for you. Now we are going to discuss its characteristics. That means its parameter: input currents, output currents, input voltage, output voltage. This we are going to measure under worst case conditions. Again, what is the worst case conditions? Like TTL. That means temperature may be maximum and voltage may be minimum, or temperature may be minimum or voltage may be maximum, and whatsoever conditions which produce the worst value of the TTL parameters, that is input current, input voltage and output voltage, and under the worst conditions how much reliably it is working, that we have to study here. So that is known as the TTL characteristics. In this one, the first characteristic which we are going to study is a floating input. In TTL also we have studied about the floating input. What is the floating input means? That means the TTL gate, or here it is a CMOS gate. If there is a more than number of inputs are there and some of the inputs are unused, which is not required to use, then that input can be kept floating. And if it is kept floating means it is not connected anywhere. It is just like disconnected from a previous signal lines. That is called a floating. So in case of the TTL, if the unused input is floating, it is equivalent to that it is a high input. So if you are not utilizing the unused input, you can kept it floating and it will act like a in high input and it will not affect the rest of the input to control the gate. But it is advisable that unused input should be connected to somewhere in a supply voltage. Either it should be connected to the VCC plus VCC positive terminal of the supply voltage, or it should be grounded, depending upon the situation that the output will not be stuck. So here also we have to connect the unused input to the supply voltage to prevent from any stray noise in the environment. And in case of the TTL, it only picks up the noise signal, and because of that the output may be changed or unwanted signal, that noise signal can false triggering the output signals, and that's why it should be connected to the supply voltage. Here it is not only producing a false triggering but also this input which is going to be floating, so excessive charge will be deposited on the input, and that is destroying that particular devices because of excessive power dissipation. So let us read through this PPT. Floating inputs. When a TTL input is floating, it is equivalent to high input. You can use the floating TTL input to simulate a high input. But as already pointed out, it is better to connect unused TTL inputs to a supply voltage. This prevents the floating leads from picking up a stray noise from the environment, RF signal from the environment. In the environment, if you try to float a CMOS input, however, not only do you set up a possible noise problem, but much worse, you produce excessive power dissipation. Because of this insulated gates, a floating input allows the gate voltage to drift into the linear regions. When this happens, excessive current can flow through the possible stages. The absolute rule with the CMOS device, therefore, is to connect all input pins, and most of or all the input pins are normally connected to the signal lines. So, in a CMOS devices, it is compulsory, it is mandatory that you have to connect all the input pins. Either they should be connected to the signal lines, or it should be connected to the supply voltage, that is plus VCC, or grounding, which will not cause any false, or it will not cause any stuck in the output. That way it should be connected. If you happen to have an input that is unused, connect it to the ground or the supply voltage, whichever prevents the stuck output state. For instance, do you understand what is the meaning of the stuck output state? That is like this. If you are having a 10 input NOR gate, and if any one of the input is connected to the 1, now output of this NOR gate is definitely going to be low. Any one of the input in the NOR gate will force its output to be low, irrespective of other its 9 input. You don't know whatever that 9 input may be there. That means if unused input is connected to the high or to the supply voltage, then output is definitely stuck to the low state, and actual input, remaining input, which may be actual input, which will not able to control this NOR gate, because output remains to be in a low state, because unused input is connected to the supply voltage. This is called the stuck state. For instance, with a positive NOR gate, you should ground an unused input. If it is grounded to the unused input, then the output is not going to be affected by that input, and there cannot be excessive gate voltage to that input, and hence the rest of the input can control the NOR gate. And that's why in a NOR gate, unused input should be grounded. So The rest of the input can control the gate according to our table or according to our input output possibility, because the retaining the unused NOR gate input to the supply voltage forces the output into the stuck low state. On the other hand, grounding unused NOR gate input allows the other input to control the output. Similarly, what happens to the positive NAND gate? Just like a NOR gate, if any one of the input is high, then output is stuck to the low state. Opposite to that, in a NAND gate, if any one of the input is low state, then its output is definitely high. And that means only one input, if it is low, it can control the total gate, and rest of the input lost their controls. That's why in a positive NAND gate, a unused input should not connect to the ground. It should be connected to the VCC, so the rest of the input can control the output. And if this unused input is grounded, then output will be definitely is going to be high, or it is going to be stuck high. So it should not be grounded in case of the NAND gate, but it should be connected with the VCC. With a positive NAND gate, you should connect unused input to the supply voltage. If you try grounding the unused NAND gate input, you disable the gate because its output will stuck into the high state. Therefore, the best thing to do with the unused NAND gate input is to tie it to the supply voltage. A direct connection is alright. CMOS input can withstand a full supply voltage. That means when it is connected to the supply voltage, you don't require a pull-up resistance like in a TTL, because it can withstand the full supply voltage even if that supply voltage may be of 15 volt. Now, the input of the CMOS can be easily damaged. How it is going to be damaged and why it is going to be damaged, that we have to study here. What is the construction of the CMOS? If we have studied already that CMOS inverter construction, between two n-channel material, n-channel conductor, there is a p-type of substrate is there, and side to that p-channel substrate there is a insulating layer SiO2 is kept, which is a totally very thin layer is there, and then there is a conductor gate is there. So between the gate and substrate there is a thin layer of insulating conductor SiO2 is there, non-conductor. Now, to have a gate voltage over a control over a drain current, that is called input output characteristics. That is, gate voltage is having a control over a drain current ID. This insulating layer must be very thin, and because of this insulating layer is there, the input impedance is very large. Actually it is infinite. So what happens when this gate voltage is controlling the drain current ID, and if the gate voltage is exceeding, then what happens, it will go into the linear regions and it will damage the gate. And that's why we have to take some prevention action for surviving this CMOS inverter. Because of the thin layer of silicon dioxide between the gate and substrate, the CMOS device have a very high input impedance, approximately infinite. The insulating layer is kept as thin as possible to give the gate more control over the drain current. Because of this layer is so thin, it is easily destroyed by excessive gate voltages. Aside from direct applying an excessive gate voltage, you can destroy the thin insulating layer in more subtle way. If you remove or insert a CMOS device into the circuit while power supply is on, the transient voltage caused by inductive kickback and other effect may exceed the gate voltage rating. So the first precautions you have to see that, and why it is supposed to be taken, because when any CMOS device is inserted or removed while the power supply is going to be on, there is a voltage spike which because of the inductive kickback is produced, and that voltage spike will damage the gate voltage. Even the picking up a CMOS IC may deposit enough charge to exceed its gate voltage rating, because when you pick up a CMOS IC, its gate will be in touch with your body, and the charge from your body can be deposited on the gate of a CMOS IC, which will damage the CMOS inverter, because it will more amount of the charge will be deposited on the gate, and hence the insulating layer is also going to be having more negative charge. N type of inversion layer is going to be produced, which will damage because of high rating of the gate voltage. Now, one way to protect against the over voltage is to include a Zener diode across the input. So, how to protect this one? Zener diode has to be inserted between the gate and ground or source. What happens? That means there is a over voltage rating is there. Lower than that Zener diode voltage, that Zener diode should be inserted so that when the excessive voltage will be there, Zener diode in reverse bias, it is going to be start conducting, and voltage across the gate and source will be always less than the excessive gate voltage rating, and this way the CMOS can be prevented. By setting the Zener voltage below the breakdown voltage of the insulating layer, manufacturers can prevent the gate voltage from becoming a destructive high. Most CMOS ICs include this form of Zener protection. Now we will see the typical transfer characteristic of CMOS inverter. So if you are having a CMOS inverter, inverter means not gate. Upper there is a P channel MOSFET and lower is N channel MOSFET, which is connected with the VCC and ground. Common drain is supposed to be the output and common gate is supposed to be the input. So you can increase the input voltage and you can measure the output voltage for different input voltage from 0.2, 0.4, etc., etc. And this way the transfer characteristic can be prepared. A graph of the input output can be prepared, which is called a transfer characteristic of CMOS inverter. Figure 14.36 shows a typical transfer characteristics input output graph of a CMOS inverter. When the input voltage is in the low state, the output voltage is in the high state because it is acting like inverter, not gate. So you can see that this graph is a typical transfer characteristic of the CMOS gate. On x-axis we can change the input voltage, so it is on the x-axis V in, and on y-axis it is called designated V out. When the V input voltage is going to be 0 volt, which is supposed to be the low state, then output voltage is going to be in the high state, that is at least VCC voltage will be there. Now you can increase the input voltage all the way like this up to a threshold voltage when the inversion layer is going to be formed. Then up to that voltage the output remains to be in the high state only. When the input voltage exceeds the VCC by 2 approximately. Then the invergence layer is going to be formed and the CMOS is going to be closed, or N-channel MOSFET is going to be start conducting, and hence the output is going to be low and output will be 0 volt. So if the input voltage exceeds VCC by 2 and if it is remains greater than VCC by 2, then output definitely remains to be in the low state, that is going to be 0 volt. This is called transfer characteristic of the CMOS gate. As the input voltage increases, the output remains in the high state until a threshold is reached. Somewhere near the input voltage of VCC by 2, the output will switch to the low state. Then any input voltage greater than VCC by 2 holds the output in the low state. This transfer characteristic is an improvement over the TTL. Why? Because indeterminate regions is much smaller. We have studied already the input TTL characteristics and output TTL characteristics. In both these characteristics, there are three windows: low windows, high window, and indeterminate window. So, indeterminate window in a TTL is very large, while indeterminate window in case of the CMOS IC is very low. And that is a main advantage of CMOS logic family over a TTL logic family. So this transfer characteristics as an improvement over the TTL. Why? Because indeterminate region is much smaller than TTL indeterminate regions. As you can see, the input voltage has to be nearly equal to VCC by 2 before CMOS output switches the state. That means until VCC by 2, the output will not swing from high state to the low state. This implies that noise immunity of the CMOS device ideally approaches VCC by 2. Typically, noise immunity is 45% of the VCC. Also notice how much better defined the low and high output states are. And very important things, in a case of the TTL, output can be when it is high, it can be any value between 2.4 to 5 volt. That means very large variation in the output is possible. But in case of the CMOS, when the output is high, it is approximately VCC only. And when the output is low, in case of the TTL, that window is from 0 to 0.4 volt. Here output is almost ground volt, 0 volt only. So output in the low state and high state is better defined in case of the CMOS compared to the TTL. When CMOS loads are used, the CMOS source and sink transistor have almost no voltage drop because there is almost no input current to the CMOS load. So when one CMOS is utilized as a driver and other CMOS is utilized as a load, output of the driver is connected to the input of CMOS load. Because the CMOS load input, which is supposed to be the gate, which is not having any input currents, or input currents is in the order of microamperes and very low. So what happens? The sink and source transistor of the CMOS driver is almost very low current is there, and because of that output is not drop, output voltage is not going to be dropped either on the sink transistor or source transistor. When the p-channel MOSFET is conducting, output voltage will be approximately as a VCC because it will work as a short circuit. And when the output is in the low state, N-channel MOSFET is conducting and it will be working as a closed switch, and output will be approximately 0 volt only. So when the CMOS loads are used, the CMOS source and sink transistor have almost no voltage drop because there is almost no input currents to the CMOS load. Therefore, the static currents are extremely small. For these reasons, the high output voltage is approximately equal to VCC and low output voltage is approximately at ground. Stated another way, the logic swing between the low and high output state approximately equals the supply voltage, a considerable advantage for CMOS over the TTL. Now, the compatibility. What is the meaning of compatibility? One CMOS can be utilized as a driver and any other CMOS can be utilized as a load. You can make a direct connection like this without any buffer stage or any other intermediate state is required. That is called compatibility because output when it is going to be high or low can be directly connected to the input and it will be considered valid high and valid low state for the load. CMOS devices are compatible with one another because the output of any CMOS device can be used as an input to another CMOS device as shown in the figure 14.37a. For instance, figure 14.37b shows the output state of the CMOS driver connected to the input stage of the CMOS load. The supply voltage is we are using plus 10 volt. The ideally input switching level is going to be plus 5 volt. So you can see in this circuit, this will work as a CMOS device which is called driver. Its output common drain, just like in a figure B, you can see that this common drain of both the N channel and P channel MOSFETs are connected as output, and this is a common gate of a CMOS load, and that is working as an input. So output of the CMOS device or driver is connected to the input of CMOS load like this one. We are using here the supply voltage VCC is equal to plus 10 volt. So output can swing between the low and high, that means 0 volt and plus 10 volt. This threshold voltage for input to swing of a CMOS inverter is VCC by 2 and hence approximately 5 volt is required for a CMOS devices to change the input state from low to high state, and that way it can switch the output state also. So when the output is in the low state, you can see that N channel MOSFET is conducting. That means it will act like a short circuit between the drain and source. Very low output impedance is there and hence output voltage is approximately ground. At that time P channel MOSFET is not conducting, it is working like an open switch and it is disconnected from the VCC voltage. That time this TTL driver input is conducting, but that input current is very low. It is in the order of 1 microampere and it is going out of this device. So input current of this TTL load is when it is going to be in the low state, that current is approximately 1 microampere in worst case conditions. This current is going out of the device from the TTL load and that's why it is said to be minus 1 microampere. Input current is designated IIL. Maximum is equal to minus 1 microampere. Similarly, when the output is going to be high, this transistor will be off and this transistor will be on. P channel MOSFET is conducting, it is working like a closed switch and VCC is connected to the output, so output is going to be high. Minimum 5 volt is required to turn on, so this will be 10 volt, so it will consider valid high state input and the current is going sourcing by this transistor P channel MOSFET to this one of 1 microampere current will be there. Since the CMOS driver has a low output, the CMOS load has low input. Similarly, figure 14.37c shows a CMOS driver has high output. This is more than enough voltage to drive the CMOS load with a high state input. In fact, noise immunity typically approaches 4.5 volt from 45% of the VCC. And here we have utilized the VCC is equal to 10 volt. So 45% of the 10 volt is nothing but 4.5 volt, and hence this noise immunity is 4.5 volt here. Any noise pickup on the connecting line between the device, that means output to the input connecting wire, needs a peak value of more than 4.5 volt to cause unwanted switching action. That means its noise immunity in the CMOS device is very fine compared to the TTL of 0.4 volt. Here it is 4.5 volt. So RF signal of peak value up to a 4.5 volt, it will not cause any unwanted switching action. Sourcing and sinking. When a standard CMOS driver output is low, as shown in the figure 14.37b, the input current of the CMOS load is only 1 microampere in a worst case condition shown on the data sheet. The input current is so low because of insulated gate, because between the gate and substrate there is an insulating layer, silicon dioxide is there, so it offers a very high input impedance, ideally infinite. And what is the current? V upon R. R is infinite, so input current is very low, and that's why it is actually shown 1 microampere current in a worst case condition. Actually current is less than that also. This means that CMOS driver has a sink current of 1 microampere in a worst case condition. Similarly, when the CMOS driver output is high, figure 14.37c, the CMOS driver is sourcing 1 microampere current, that is P-channel MOSFET of a sourcing transistor or a driver is sourcing 1 microampere current to the requirement of worst case input current when the input is high. In symbol here, the worst case input current for the CMOS devices are, which is given in a data sheet. IIL maximum is equal to -1 microampere current and IIH minimum is equal to 1 microampere currents. First I capital stand for in current, second I stand for input current, and when the input is low, IIL, and maximum in worst case conditions, this current can be 1 microampere current and it is going out of the device for the load, CMOS load. So it is shown by minus sign. And IIH minimum, that means input current, when the input is in high state, that is maximum current in worst case conditions can be 1 microampere current. It will go into the device, so it is positive. We use these values to calculate the fan out. What is fan out? Driver output of the CMOS can drive how many CMOS loads without destroying any CMOS load or without operating CMOS without our Hall switching action or currents. That is called fan out capability. The fan out of a CMOS device depends on the kind of load being driven. In section 14.11, we discuss CMOS devices driving TTL devices. So it is also depends upon that what kind of load CMOS is driving. It can drive a CMOS to CMOS load also. It can drive CMOS to TTL also. It can drive to the relay, switch, etc. also. So this kind of things which we are going to study in a next lecture, that is 14.11 section. Now we want to concentrate on CMOS driving a CMOS load. So here we are going to study limited to CMOS is a driver and CMOS will be load. So it is connecting CMOS to CMOS only. How many CMOS loads can be connected to a CMOS driver for a reliable operations is known as a fan out capability. Data sheets for the CMOS C00 series devices gives the following output currents for the CMOS driving CMOS loads. So output current capacity of CMOS driver when it is going to be high and low, it is given by data sheets, and that is like this. IOL maximum, that is equal to plus 10 microamperes. So I stand for the current, O stand for the output current, L stand for when the output is low, and in worst case condition maximum current, it is going to be sinking. So lower transistor when is conducting and hence it is sinking the current, maximum current it can sink in worst case condition is going to be 10 microampere current going into the device. That's why it is a positive sign. And when the driver output is going to be in the high state, that is called IOH, output current when the output is in the high state. That means P channel MOSFET is conducting and it is a sourcing maximum current in the worst case condition is going to be 10 microampere in worst case condition according to the data sheet. Since the worst case input currents of CMOS device is only 1 microampere, the CMOS device can drive up to 10 CMOS loads. Therefore, you can use a fan out of 10 for CMOS to CMOS connections. This value is reliable under all operating conditions. That means with the VCC, a different value of the VCC as well as different value of the temperature. These values are reliable. It will give you guaranteed operations by the manufacturer. Now, there are certain test questions which you can understand. If you have studied this lecture properly, you can understand and answer these questions. So, I have put it here. Test questions. Question 1. What kind of transistors are shown in figure 14.33? That is a CMOS NAND gate. So, transistor Q1 and Q4 is a P channel MOSFET and transistor Q2 and Q3 are N channel MOSFET. In a figure 14.34a, there is a CMOS NOR gate is there, and CMOS NOR gate which is having transistor Q1 and Q2 is a P channel MOSFET and Q3 and Q4 which are supposed to be N channel MOSFET connected in parallel. Q1 and Q2 are connected in series. Why must care be taken when using CMOS devices? So many things we have seen that. By replacing a CMOS, power supply should be off, so inductive current cannot destroy the CMOS because of the excessive destructive voltage deposited on the gate. Then Zener protection is required and that Zener voltage should be lower than the breakdown voltage of CMOS devices. What is the transfer characteristic of the CMOS inverter? Input and output relations, input voltage and output voltage relations of the CMOS inverter is known as the transfer characteristic of the CMOS inverter. Thank you very much, friends.